insert into a binary size tree. You are given the root node of a binary size tree, BST, and a value to insert into the tree. Return the root node of the BST after the insertion. It is guaranteed that the new value does not exist in the original BST. Notice that there may exist multiple valid ways for insertion, as long as the tree remains a BST after insertion. You can return any of them. So we have we have this tree over here, and our value is 5 to insert into it. So in a BST, the lower child is always the left child is always lower than the right child. So it's 5. If 5 is lower than so if the bar is lower than 5, we go this way, and it's higher this way. So since 5 is higher, we go this way. So and then from here, since this is 5 is lower than 7, we go. It will be its left child. A new left child will be created where it will be inserted, and okay. Let's copy and paste this our goal so that we can keep an eye on it. So let's get into our time and space complexities. We will do this recursively. Recursive approach. Time and space complexities. This time complexity is log n for a balanced 3 over n in the worst case, which will be skewed 3. Best case. So let me copy and paste this. Copy, space, complexity. So we'll solve this recursively. Let's expect an indent. Let's see. Boom. I'm not sure where they came from. It is indented. So let's just get into this. So if we don't have a value where our root is none, where our root is, let's enter it. Return. So what's the name? 3 node. I'm gonna put a value in var. If it's empty, put var in. So now let's look at our thing, our problem. So let's make our if condition. If our val is is less than our root val, then our let's call on this recursively insert self enter into BST, and then put in the root dot left, and then a value let's assign that to our left, root dot left. Else, if it's larger, self dot insert, just so that I mess this one over here. Insert into BST, go dot right, and if I put it inside and assign it to root dot right equals to. So if val is greater than the val. So now we have we're going to recursively call on whichever is lower than our root. If it's lower, we go left. So since it's lower, it's high. Since it's high, we come here, and then lower, we come here again. We will move to left, and then let's return our what are we going to return? Our root. That's the weird, and let's see if it's going to work out on our first try. Yes, and we have been successful on our first try. Let's see if it will pass all cases. It should pass all cases, and it's been able to pass all cases. And that's it for this one. It's somewhat easier with the recursive function that we have.